All right, we just looked in some detail at the titration of a weak acid with a strong base. The titration of a weak base with a strong acid is very similar, but has kind of the downhill slope instead. So if we titrate it, the half equivalence point is going to be where the POH equals the PKB. And then the equivalence point, again, the conjugate acid in this case is going to take over, and so it's going to be slightly acidic. Let's practice the titration of 25 milliliters of 0.10 molar ammonia. The PKB is 4.75 with 0.1 molar hydrochloric acid. Calculate the pH of the solution at equivalence. So at the equivalence point, we have neutralized all of our ammonia. So we have equal concentrations. They're both 0.1 molar. So we know our final volume is going to be 50 milliliters. We are going to have all of our ammonia has gone over to NH4 plus. And so if we started off with, so 25 milliliters times 0.10 molar gets me 2.5 millimoles of my NH4 plus in my 50 milliliters. And so my concentration of NH4 plus is 2.5 divided by 50, 0.050 molar. Now my NH4 plus water is in equilibrium with H3O plus NH3. I know I have 0.050 molar of this, 0 of those to start with. Again, we're doing, oh, sorry, this is minus X over on this side. But X is small, so we're going to ignore it over there. Now I need to find my Ka value for my ammonium. I know my PKB, so my KB is going to be 10 to the negative 4.75, which means my KB is 1.78 times 10 to the minus 5. But I need my Ka for this one. So my Ka is going to be my Kw, 1 times 10 to the minus 14, divided by my Kb, 1.78 times 10 to the minus 5. So my Ka for ammonium is 5.62 times 10 to the minus 10. And my Ka then is equal to x squared over 0.050. So my x is 5.3 times 10 to the minus 6, so which is my H plus or H3O plus concentration. So my pH is the negative log of that, which is 5.28. Okay, so to review, what I did was I figured out how much conjugate acid I made when I was at my equivalence point. I took my Kb, converted it into a Ka, then solved for my concentration of H3O plus and found the pH from that. What about polyprotic acids? If the difference in Ka values is significant, there's going to be 2 equivalence points. The closer they are to each other, the harder they are to see. And the volume from one equivalence point to the next equivalence point is equal to each other. So in this case, it's both 25 milliliters. So it takes 25 milliliters to get rid of the first H plus, then another 25 milliliters to get rid of the second one. So polyprotics, you're going to see this 2-bump system where then you can find your pKa1 and your pKa2 by finding the halfway point, the half equivalence point in between. Okay, so another practice one, a 0.229 gram sample of an unknown monoprotic acid is titrated with 0.112 molar sodium hydroxide. The resulting titration curve is shown. Determine the molar mass and the pKa of the acid. So take a minute, think about that. How would you approach it? First thing I would do is find my equivalence point and my half equivalence point. My pKa is the pH at my half equivalence point. So I'm going to say that my pKa is around 2.5-ish. It's hard to tell from this graph. Then the molar mass, we know at our equivalence point, we've added, that looks like 25 milliliters of 0.112 molar sodium hydroxide gets me 2.8 millimoles of acid. Well, technically 2.8 millimoles of base, which is equal to the amount of acid that I started with. And molar mass is just grams per mole. So I have 0.229 grams is actually, let's just do this, I'm converting my millimoles over to moles, so it's going to be 2.8 times 10 to the minus 3 moles. If I do that math, I get an answer of 81.8 grams per mole. So 82 grams per mole, my pKa around 3. That's fine, depends on how you draw it. Mine would round up to 3 if I did 1 sig fig. So that's how you would use a graph to determine things like how many moles of acid you have, what the molar mass is if you're given a mass for it, and what the pKa is.